Well, we've discussed the general history of the solar system, and we're going to start now a process of trying to look at some of the outcomes and what we find in it today. And a natural place to start is the planet we know best, the little blue marble we live on. Pedagogically, this makes sense because it's going to be interesting to see what the physics we understand and the natural history of the solar system that we've learned tell us about living on Earth. Scientifically, intellectually, it makes sense because we know more about Earth than about any other planet. Whatever theories we develop should first be tested where we can actually measure things, which is on Earth. So let's do a quick pass. Of course, Earth sciences is a huge field that I wouldn't be qualified to teach even if I had the time, but let's do a quick pass and see what we can say about Earth as a planet. So first thing you see when you look at Earth is that most of its surface is covered with liquid water. As we know, that means that it has an atmosphere because liquid water can't exist without it. And indeed, the Earth is covered with an atmosphere, mostly nitrogen, about 20% molecular oxygen. And then below both of those is rocky surface, a crust, which is made mostly of silicates. Now, we don't expect this to be a good description of the composition of the entire Earth because the Earth melted. We see that it is round because it melted. This means it underwent chemical differentiation. We expect the inside of the Earth to be different chemically and structurally than the outside. And indeed, we find that the Earth has an inner core which is rich in iron and nickel and heavier materials. And then the silicates that make up the crust of the Earth also make up the layer below the crust, which is called the mantle. And so we have the very densest, heaviest elements having sunk differentially to the center and formed a core, and outside that mantle. Now, this gives the Earth an average density of 5,500 kilos per meter cubed, remembering that rock is about 3,000 kilos per meter cubed. This is your first indication that there's something denser underlying the Earth. The Earth is an equilibrium system. Gravity, as we remember, is trying to crunch it down. The Earth is at least mostly a fluid. It is not a rigid object held up by its tensile strength. The reason that Earth does not collapse under the force of gravity, just like our slinky, is that pressure increases as you go deeper down into the Earth, each layer holding the layer above it against the force of gravity. And so as you go down into the Earth, pressures become very, very high, densities become very high. We have pressure is so high at the center of the Earth that despite the fact that, as we'll see, temperatures are very high, the center of the Earth is essentially solid metal. That's the inner core. This is surrounded by an outer core of liquid metal. And you can see on the graph at the bottom of the slide the jumps in density as a function of distance from the core. Distance from the center increases to the right, and density is the vertical axis. And you see the different layers of the Earth: an inner solid core, a slightly less dense liquid outer core, a mantle that is essentially molten rock, and floating above all of it, the crust. How do we know so much about the internal structure of the Earth? Nobody's ever been there. Well, it turns out that we can learn a lot about the mechanics and the structure of something by the propagation of sound waves. Earthquakes generate sound waves that propagate through the interior of the Earth. We can measure them way over on the other side of the Earth. Studying the time delays and the intensity patterns with which they propagate teaches us a lot, and in particular indicates the size and mass fraction of the inner core, which is solid, and the outer core, which is liquid, because they have different properties as regards sound propagation. So we think we understand the inside of the Earth, and one of the things that we know is that not only pressure and density increase as you move deeper into the Earth, but temperature. The inside of the Earth is an extremely hot place. Even the mantle is very hot. And so what generates this heat? Well, there's a Kelvin-Helmholtz heat that heated the Earth as it was forming, remember, because gravitational potential energy was being converted into heat. But it turns out that the dominant heat-producing process in the Earth today is radioactive decay. The heavy elements, which are the ones prone to radioactive decay, would have sunk under chemical differentiation and are concentrated in the core. So the core is generating heat, and this heat is carried up through the mantle by convective processes. We have here the process that we said we might discover someday, where we have a fluid, the mantle, heated from below by the hotter core, by the radioactive and to some extent still Kelvin-Helmholtz processes going on in the core. And so this causes warm fluid to rise in some places, cooler fluid to sink in other places, and sets up these circulation cells in which, convection cells, in which the fluid circulates. This has several effects. One is it carries the heat out from the core, heating the surface. The surface loses heat to radiation. Every square meter of Earth loses about 87 watts, about the amount of energy it takes to run an average light bulb, to radiation because of inner heating. 80% of that is radioactive. The other effect, of course, is that the horizontal component of the flow at the top of the mantle drags the crust around. Earth's crust is broken into plates, and the motions of these plates tell us a lot about the nature of geological processes on Earth. The fact that Earth has this plated crust and that these crusts are moving leads to recognizable features. For example, the mountain ridges, the linear ridges of mountains, the Rockies and the Andes, that line plate boundaries where plates are coming together and one of them gets pushed up, or the Alps and the Himalayas. These are linear mountain structures that reflect the fact that plates are being crunched together. On the other side, when two plates come together, one of them will typically fold up, the other will fold under, and crust will be subducted. And the result of this plate tectonic process is that the Earth's crust is by and large very young. This is why we never found old rocks on Earth. Not only are features on Earth, mountains and valleys, subject to erosion by air and water and natural processes, but the very atoms that form the crust are, in a geologic sense, very young and constantly being interchanged. Crust is constantly subducted and reabsorbed into the mantle, and then new crust is constantly formed by volcanic processes. So we have heat rising from the bottom, and then heat being radiated out into space, and this is the beginnings of Earth's energy balance. Of course, if Earth relied on internal heat, it would have been a very cold place by now. It's been around losing energy for billions of years. What keeps Earth from freezing is the sunlight. So we can set up an understanding of what maintains the constant temperature of Earth by setting up a sort of balance problem. Earth absorbs energy from sunlight as radiation, with this additional small contribution from internal heat. But if you remember that every square meter of Earth absorbs about 1,300 watts in sunlight, the 100 watts in internal energy is not a big deal. At the same time, Earth is losing heat because it's a dense object sitting in space. It has a temperature. It radiates a black-body spectrum out into space. If Earth is too hot, if Earth gets warm, it radiates more because of the Stefan-Boltzmann law, and that cools it down until the rates are equal. If Earth gets too cool, its Stefan-Boltzmann radiation decreases, and then that causes the sunlight to continue to heat it. In equilibrium, this is a stable equilibrium, and one expects the rate at which Earth absorbs energy and the rate at which Earth loses energy to be equal, and we can use that to figure out how warm Earth should be. So, Earth is a dense object. As a first approximation, let's imagine the Earth as a black body. How does this work? Well, here's the Earth. It's a sphere of radius r, and it's orbiting here in space, and if I imagine that the sun is over to the left, then there is a flux of sunlight impinging on the Earth from the left, and this flux is given by the solar constant, which is related to the solar luminosity, by our energy conservation relation that says the solar flux is distributed uniformly over a sphere whose radius is the distance from Earth to Sun, so d here stands for 1 astronomical unit. Now, how much of this light does the Earth absorb? Well, it's clear that only half of the Earth at any given time is absorbing any light at all, because the right half of the Earth is not absorbing anything. But it's also true that radiation is not uniformly absorbed, depends on where you are on Earth. In this equinoctial configuration, light is absorbed most efficiently at the equator, and this is easiest to understand by realizing that if I replace the Earth by this disk, which sits perpendicular to the direction to the sun, and has a radius equal to the radius of the Earth, then this disk would produce the exact same shadow over to the right as does the ball that is the Earth. Basically, if I chop off everything but the central disk, then I am not changing the shadow. And so effectively, as an absorber, the absorbent area of the Earth is the same as the absorbent area of this, as the actual geometric area of this disk, which is just pi r squared. Now remember that the full surface of the Earth is 4 pi r squared, but it absorbs as though its area were pi r squared. And so now I have the area, I have the incoming power per unit area, and the total rate at which Earth absorbs energy from the Sun, therefore, is pi r squared times the solar luminosity divided by 4 pi times the square of the distance to the Sun. I can improve upon that calculation because the Stefan-Boltzmann law tells me that the solar luminosity is equal to 4 pi times the radius of the Sun squared, that's the surface area with which the Sun radiates, times sigma, the Stefan-Boltzmann constant, times the fourth power of the solar temperature. So I can plug this into that, and I obtain, when I put this expression into there, I get pi times the radius of Earth squared times 4 pi's cancel all over the place, times sigma, fourth power of the solar temperature, and then I get the radius of the Sun squared divided by the distance to the Sun squared. So this is my expression. I will rewrite it more neatly, but this gives me an expression for the total rate at which the Earth receives sunlight. Some pi's have been cancelled, and I've rearranged the factors slightly, but notice that this depends on both the Sun's size and temperature and our distance from the Sun as well as the radius of the Earth. Okay, this is the rate at which Earth would absorb energy. How about the rate at which Earth loses energy? Well, that too is not too difficult to realize. The Earth is a black body. It has a temperature, T Earth, and if the Earth is at some temperature, then each square meter of Earth radiates, according to the Stefan-Boltzmann law, at the rate sigma T to the fourth into space. Multiply that by the radiating area of Earth, which is the full surface of Earth, since Earth radiates in all directions, and that will give you an expression for the rate at which Earth loses energy by radiating it out to space. And so, again, rewriting that more cleanly, we have now an expression, and thermodynamic equilibrium will determine the Earth's temperature in such a way that these two quantities are equal. So my job is to equate this to that. That will give me an equation for the surface temperature of Earth in terms of properties of everything else. And let's see, well, we have some cancellations here. Fortunately, the sigmas cancel. That's good. I don't need to remember the value of sigma. The pi's cancel. Most importantly, the radius of Earth cancels. The size of Earth is completely irrelevant. Any object, asteroid, Jupiter, Earth, whatever you put at Earth's distance from the Sun will have the same equilibrium temperature. And rearranging things, I find an expression that says the temperature of Earth to the fourth power is the solar temperature to the fourth power times this ratio, the radius of the Sun divided by the distance to the Sun. And then I want to square this, so that 4 will turn into a 2 when I put it inside the square. And this tells you, note I computed for Earth and Sun, but any object in equilibrium with the radiation of any star, if you know the temperature and size of the star and your distance from the star, you can compute your equilibrium temperature. So now I can apply this to Earth, and I find 279 Kelvin. This is about 6 degrees Celsius. That's pretty chilly, but the first thing is that it's not outside the ballpark. A rough approximation of Earth as a black body in equilibrium with sunlight has given us a temperature value that is not outside the range of what is actually the temperature on Earth. We're on the right track. Maybe we should try to improve our approximations. Well, we know one approximation we've made that is clearly false. We've assumed that the Earth is black. What that means is that it absorbs all of the incoming sunlight and emits thermal radiation with Earth's ambient temperature of around 300 Kelvin. This is obviously infrared radiation. We can use Wien's law to figure that out. And what this means is that if Earth were really black, viewed from space, emitting only infrared radiation, it would be a black object. We've all seen the beautiful pictures of Earth from space. Earth is a beautiful blue marble. How does it get to be blue? Well, the reason Earth is blue is because some of the sunlight, the visible sunlight that impinges on Earth, in fact, is reflected by cloud tops, by oceans, by Earth's surface. This fraction, about a third in the case of Earth, is called the Earth's albedo and denoted by the letter A. It is a property of any astronomical object that some of the light impinging upon it is reflected, and albedo is the term we use to denote this property. Now, with Earth's albedo of about a third, that means that the amount of the sunlight that goes to heating Earth, the amount of sunlight that is absorbed by the Earth heating it, is only about 2/3 of the incoming light. That means that the amount of light Earth absorbs, which we will denote by I absorbed, is only about 2/3, a fraction 1 minus A, of the incoming radiation. And so, when we take that into account, what will that do to Earth's temperature? Earth is absorbing only about 2/3 of the solar radiation that falls upon it. That means to be in equilibrium, it must emit about 2/3 of the amount of energy that we used previously to compute its temperature. Oh, this will make Earth cooler, because to emit less, it must be cooler. That's what the Stefan-Boltzmann law tells us. Since the power radiated is proportional to the fourth power of the temperature, to reduce the emitted power by a factor of about 2/3, we'll have to reduce the temperature of Earth by a factor of about 2/3 to the 1/4 power. So the T to the fourth is 2/3 of what it previously was. Inserting that, we find a prediction for Earth's temperature of 254 Kelvin. This is not an improvement on 279. 254 is well below the freezing point of water. If this were really the ambient temperature on Earth, life here would be very different than it currently is. Luckily, this is not correct for Earth. We will turn in a moment to discussing how Earth's atmosphere allows us to actually enjoy temperatures quite a bit more balmy than 254 Kelvin. But let us stop here and note that for a planet without an atmosphere, for example, were we to be discussing the Moon is about at the same distance from the Sun as Earth is. The Moon does not have an atmosphere. We would expect the average temperature on the Moon to be about 254 Kelvin. And for any planet orbiting any star, if we know the star's temperature, the planet's albedo, and its distance, and the radius of the star, then we can compute a predicted equilibrium temperature for that planet.